So in the last class, I basically uh, introduced you to the genome assembly problem, which can be abstracted as the exploding newspapers problem. So basically, each genome can be considered as a full edition of a newspaper. And now let us say if these newspapers were stacked, copies of these newspapers were stacked, they were blown into pieces. And from these pieces, you have to piece together what was one copy of the original newspaper. So here we were looking at this newspaper at a certain date. Now, essentially what you'll be having is you'll be having overlapping fragments of the newspaper, right? So this, you can see that at shirt, the shirt seems to be common app approximately, right? So now when you, like a puzzle, when you overlap these things together, the words, sentences start to make more sense. And like that, you can overlap these pieces and can reconstruct the genome. They can reconstruct the original newspaper. So this is essentially what we do in the genome assembly problem. You have a genome which is fragmented into randomly fragmented into smaller DNA fragments, which you overlap and you try to reconstruct the original genome sequence. So this was the newspaper that was published in 27 June 2000. That was the announcement of the human genome. So again, how does the genome assembly look like the exploding newspaper problem? So just like the newspaper, you have the complete sequence of the genome. You have multiple copies. You always start with multiple copies because you want to have overlapping fragments when you are randomly breaking this genome. So therefore, you would break these multiple copies of the same genome into smaller fragments, and then you will overlap these fragments and then would reconstruct the original genome. So typically, the reason why you do this is that because there is no technology currently which can read the nucleotides in a genome like you would read a book, that you will go from the beginning of the genome till the end of the genome. People are trying to make these technologies. Maybe in the next few years, you might see something like this. So the best way to actually, since we cannot look at a single molecule, so you have to look at multiple copies of the same molecule that have been fragmented into smaller pieces, and then you overlap these smaller pieces. So typically the protocol that researchers use is that they take small tissue or blood samples containing millions of such cells. Now, when you take a tissue or millions of like any sample which has millions of cells, one assumption, which is a fair assumption, is that all the cells coming from one individual is going to have the same DNA, is going to have identical DNA. So when you would be precipitating the DNA by breaking the cells, you would essentially be getting these multiple copies of DNA molecules. Now they can be fragmented into smaller fragments, like I showed you earlier in the genome sequencing technologies module, and then you can do the sequencing and can assemble these things together. So in order to formalize the problem, I introduced you to the idea of the string reconstruction problem. So the genome can be considered to be a string, and to reconstruct the string from its fragments is essentially called the string reconstruction problem. So here there are certain assumptions, the assumptions being that whenever you are breaking the genome, you would have a perfect coverage. That is, the genome, you will have small fragments of the string which would be representing, so you'll be having all the small fragments that can be possibly generated. This might obviously not be the case. There will be no errors in sequencing, right? So the way that you define the string reconstruction problem is that if a genome is defined as a string text, right? You can divide this genome into small k-mers. These k-mers would be corresponding, they would basically be like reads. So by doing this, you can essentially define the k-mer composition of a text. So k-mer composition of a text is all the k-mers, a set of all the collection of k-mers which are substrings of the text. So the composition K of a text, so composition 3 of a text shown here, are all the three-mers which are formed in the text. Typically, you will be representing these k-mers or these substrings in the lexicographic order. That's why we start from A and we end with T. So the string reconstruction problem essentially is you have to reconstruct a string from its k-mer composition. So the input is k and a collection of patterns of k-mers, and the output is a string text, right, which is whose k-mer composition is equal to the patterns of k-mers that you've been given, if such a thing exists. So if I'm giving you the k-mers like this, so you can already start to see some patterns. There is AAT and TAA. So basically TAA and AAT overlap. So it will be a TAAT here. Now you have to look for AT. There is a AT here. So you can add a TAAATG. Now you have to look for a TG. There's a TG here. So there's a T here. And then you have to look for a GT. So you will essentially overlap, right? So just like that, TAA, AAT, TG, TGT, and GTT. And you basically overlap them and you reconstruct the original string. So when you do this, you are essentially forming what's called an overlap graph, and you represent each of these k-mers as nodes, so these circles or ovals, and the fact that they are having overlapping k minus 1 mers. So basically, if the suffix, that is the last k minus 1 mer letters, are equal to the prefix, that is the first k minus 1 letters are common. So for example, here AAT, in this AAT and ATG, AT and TG, AT and AT are common here, are the prefix of a suffix for AT, and it's the prefix for ATG. So therefore you draw a line connecting these two. So you draw an arrow connecting these two. So this gives you what's called a directed graph, where nodes are your k-mers and the edges or these arrows are essentially the fact that they share prefix and suffix. Now, when you have to reconstruct the original genome, you have to basically find a path in this graph which is touching each k-mer, each node once. All right, so such a path is called a Hamiltonian path, uh, because it was basically, this was a mathematical problem formulated by a mathematician called William Hamilton. So if you would have gone back and seen this kind of finding a path, one problem is, where do you begin? So can somebody tell me why have we begin with TAA here and not any other node in this graph when you are making this?
Sir, it does not have any incoming arrow.
Exactly, it does not have any incoming arrow. That essentially means that it is going to be the first k-mer that is generated, right? Because it does not have any prefix. So that's good. The other thing that you would have noticed that I talked about in the last class is, because there are certain repeats here, so ATG is repeated. Because of this, you are actually not going to have a single unique path. You might actually be touching all the nodes, and you might actually be have a completely different sequence that you might actually find out. So because of this, as I will tell you later on, Hamiltonian representing or doing the string reconstruction problem by using this kind of a data structure, where you represent reads as nodes and the edges as connections between those nodes or overlaps between those nodes, is not the most ideal solution, because this falls in the category of more harder problems to solve, because there can be many such paths existing. So in order to overcome this, I'm going to introduce you to another data structure, which was given by two mathematicians, Jack Good and Nicholas de Bruijn, which is called the de Bruijn graph. So de Bruijn graph essentially is doing something similar, but in a different way. So I'll show you. So this is essentially you, instead of saying representing your nodes as k-mers, you represent your edges as k-mers. So earlier we had TAA as the first node, but here TAA becomes the first edge. And correspondingly, the nodes now become the k minus 1 prefix and suffix that is shared between two edges. All right. So in this case, the the first node would be TA and the second node would be AA, right? Similarly, you will be filling all the other nodes. Okay. All right. So given a set of k-mers, first each k-mer would be now broken down into two nodes corresponding to the prefix and the suffix of that k-mer, and an edge will be drawn between those nodes which would represent the k-mer itself. Okay. So this is a simple flip in how we represent the data, and you will see that this is going to change dramatically how genome reconstruction can happen and simplify the problem a lot. Okay, so unlike the overlap graph, the idea is that you would like to glue together the nodes which have the same labels. Okay, so in order to reduce the size of this graph, in the overlap graph, you were essentially uh, drawing an edge whenever you had the same suffix and prefix. But here, because that was the overlap, right? So overlap was represented by the edge. But here the node itself represents the overlap. So you get the added bonus of doing this representation that you can actually simplify this graph into a smaller graph. So how does it look like? So all the nodes which are similar, they can be glued together. So ATG was coming thrice. So you can take all the ATs and you can glue them together. Similarly, you can take all the TGs and you can glue them together. Then there is a GG here, right? There was a GGG, a tremer, and you can basically glue the two GGs together, and then this becomes also a sort of a reduced graph. Okay, and the number of edges between the nodes represent how many times that specific k-mer was found. All right, is this clear to everybody so far? So I'll go on. So this particular graph is called the De Bruijn graph for the same text that we did. Again, we will start from the edge which does not have an incoming, as we'll start from the node which does not have any incoming edge, and we should end at a node which does not have any outgoing edge. Okay, so now when you go through this, you essentially follow the arrows. You go like this, then you maybe go like this again, right? And then you end here. So the goal here of in the Hamiltonian or in the Hamiltonian cycle or the overlap graph, the goal was to touch each node once. But here the goal would be to touch each edge once. Okay, because each of these edges are actually representing the k-mers that you have. All right, is this clear to everybody?
Yes, sir.
So now as an exercise, I would ask you to construct the k equal to 4 and k equal to 5 mer graphs for this particular string. I'll give you a couple of minutes for this. So this is how k equal to 4 graph would look like. You can see that the graph becomes simplified a bit because you don't have these kind of loops. The number of edges reduces, obviously. The graphs and k equal to 5 becomes even easier, even simpler. And typically the graph is becoming less and less tangled. So this is something that you would also see in the case of the overlap graph. the in larger K you have, the lesser number of overlaps you would have to represent as well, right? So this is akin to essentially saying that when you are doing sequencing, you are having longer and longer read length for your sequencing results. All right, whatever technology you're using. So typically, therefore, people are trying to come up with sequencing technologies where the fragment length or the DNA read length is longer. Okay, but now do you feel that you have basically an idea? If I give you a text and a K, you can quickly make a like a De Bruijn graph. Do you see some like
Yes.
a basic idea coming up? So I'll talk about that basic algorithm of how to do this. Okay, so let's say that, so here again to repeat, the genome path is the path which touches each edge exactly once. This is called the Eulerian path, and this path defines the actual original genome that was represented. Okay, so can you construct the De Bruijn graph if you don't know the text already? So let's see if we can do that. Let's say you have been given lots of k-mers like this. Okay, so this, by looking at it, you can clearly say that this is a k equal to 3 mer graph, right?
Yes,
Yes,
sir.
sir.
So now the same idea that you used to create the De Bruijn graph, to converge the De Bruijn graph, you can also apply here. So whenever you see two nodes which are similar, you just keep on gluing them. Okay, so let us start with the first one. So CC and CA. Do you find CC somewhere? You find CC here, right? That means you are going to glue this particular part of the graph with this particular part of the graph. All right, then you will find CA. There is a CA here. So you'll glue this like this. Okay. So now you have a simple algorithm that given you k-mers, you deconstruct those k-mers into two nodes and an edge between those two nodes. And then you have a simple iterative algorithm which keeps on gluing the nodes when they are similar and stops when there is nothing more to glue. Okay, so this is what you will be obtaining. Now, when you would be looking at the same thing, say, like doing the same idea, so you will start with the node which has no arrows coming in, so TA, and you will want to end on the node which has no arrows going out, so that's TT. And now when you will be looking at, when you will try to go through this graph, you will observe that there is only one unique path, actually, unlike the Hamiltonian. Okay, so this is the basic idea of now changing the problem on its head. Instead of defining nodes as k-mers, you define edges as k-mers. Instead of saying that you would want to have an algorithm that tries to visit each node once, you try to have an algorithm which visits each edge once. All right, so that's the simple difference between a overlap graph and a De Bruijn graph. Okay, so it's basically the same graph that I showed you. So the approach for constructing the De Bruijn graph: form a node for every k minus 1 mer appearing as a prefix and suffix in the k-mers that you've been given. And for every string in the patterns, you connect the prefix and suffix, right, which are common. And you keep on doing it until there is nothing more to connect. So you can verify that these are the patterns which are represented here. So now keep, like, the reason why I want you to verify this so that your eyes are getting used to it, because these are the kind of problems that you can expect. So let us say if you want to look at AAT, you want to look at nodes AA and AT. So AA and AT are there. ATG, so you have AT and TG there. AT and TG somewhere, yes. Then you want to look at CAT, you have CA and AT. You know that AT is already there, so you would be having it. CCA, so CA is there, you just need to look for CC. You already have AT, so you need to look for GA. So GA is there and there is a connect with AT, right? So on and so forth. So you can quickly verify whether the patterns that you've been given are actually represented in this graph or not. Okay, so now which graph would you use? So this is the overlap graph where you have to find a Hamiltonian cycle, and this is a De Bruijn graph. where you have to find a Eulerian cycle. So can you already see something? Immediately something popping out for you? The difference between these two graphs?
The drawing graph is much less complex.
It's much less complex. It has much, when you say much less complex, that means it has less number of edges and it has less number
Yes,
of
sir.
nodes,
And less number of connections as well, like
right?
overlaps.
So now, is it obvious to have less number of nodes? Isn't it obvious that it would have less number of nodes?
Yes, sir, because it's a like pair of two instead of a pair of three.
Pair, or it's basically, so the number of each
It's
node theoretically is,
Basically, so the number of repeats. So there are many repeats in the sequence. So that's why there are no small number of nodes in de Bourgeois graph.
no, that's not, it's very much easier. So there are more number of threemers or there are more number of twomers,
yeah. Yes, sir. So like there are like 4 to the power 3 possible three-mers, but only like 16 possible two-mers.
right? 4 to the power 2. So basically the size of the graph is one order less. And as a result of which, you'd also see that the number of edges that you have in the graph is also much less, right? So that definitely reduces the problem. Now, when you actually try to solve these graphs, you are trying to solve two problems that were put forth by the respective mathematicians, Hamilton and Euler, right? And I'm going to discuss those problems. So the first problem was put forth by Hamilton. So it's basically, this is a game, as I will show you in the next slide. So this is a graph, right? Like the other graphs that I showed you. This is probably some of the questions that you might be seeing in one of these competitive exams or like in some of your job interviews. So can you quickly find the Hamiltonian cycle in this figure? And while you find the cycle, can you think about how to find a cycle in any given graph like this? I'll give you a couple of minutes. Anybody has found a cycle? Please show me your hand. I hope people are trying. So remember,
So I guess we can just take like one node either from the outside or from the inside, and then we can work our way from the outside to the inside or from the inside to the outside. Sequentially.
okay, would it always be possible? But in this case, there is a structure to the graph, right? Out to in. But the graphs that I showed you earlier, they did not have a structure like that. So you would have to first represent your graph in this kind of a out to in structure, right?
Yes, sir.
I mean, this is a path, right? So you're partially correct. I mean, not partially correct. I mean, this is how it was solved. You start from the we start from, where did you start from? Actually, this is a complete cycle. So you start from here and you start to go in, then you go out, and then you complete the cycle. Okay, so this was called the Icosian game, and you have to basically, where you start, you place the number one, and in the next one you place number two, so on and so forth, so that each adjacent number represents a connection. So this was the original game. Now the other opposite um, game that was, or sort of problem that was thought of, was the bridges of Königsberg. This was done by Euler. So Königsberg has this interesting it's a place in Europe which is interesting kind. It has as a river island. So basically there is an island in between and there is a river which flows around this island and you have 7 bridges. So Euler was thinking, can I walk? I want to optimize the time that I am here, and bridges. This city is famous for bridges, so I want to only visit each bridge once. So can I come up with a mathematical argument or way to find the best path so that I only have to visit each bridge once? So there are 1, 2, 3, 4, 5, 6, 7 bridges. So there are basically 1, 2, 3, 4 and 5 sorry 4 land masses which are connected by these bridges. Okay, so each of the land masses is a node and each of the edges is a bridge. So you can essentially define a graph like this. So the middle one is the node green and this is connected by 2 bridges to this landmass. So you form 2 nodes there. This middle one is connected to this landmass, so you have two nodes here, and this orange one is connected by one bridge like this, one bridge like this, and one bridge from each of the other landmasses. So this was the solution. So when you have, so if you want to essentially visit each bridge once, what you are looking for is a Eulerian cycle. Now, can you see if a Eulerian cycle exists for this particular graph? What is the maximum number of bridges you can non-overlappingly? You don't have to repeat.
So I guess 6.
Okay. So, but you can you, there are 7 bridges, right? So you don't have a Eulerian cycle? Is everybody getting to the same answer? Deepak?
Yes, sir. 6 bridges.
So we need to visit one bridge twice to go through each bridge.
To go through each bridge. So when Euler about almost about 300 years ago now, when was thinking about this problem, he actually came up with a way to solve it. So you are right. This is just an Euler path does not exist in this graph, and it does not exist in this graph because this graph has certain peculiar properties, and those properties have to do with how the graph is connected. Okay, so there is no solution because some nodes have odd degrees. So that basically mean that the number of incident edges are odd. So here there are 3 edges, there are 3 edges, and here there are 5 edges. So whenever you have odd degrees, typically Euler paths are not existing. Okay, so Euler actually by doing this, he came up with a way to say that when is it that you would actually have a path or a Eulerian cycle existing. So the key idea for the algorithm that he came up with was that this, the checking whether an Euler path exists was a simple algorithm that could be finished in polynomial time. All right. But on the other hand, the Hamiltonian cycle problem, that problem that came actually after the Euler problem, so far people have not been able to find a way to solve this problem in polynomial time. So these problems, which are non-polynomial time problems, but have a solution existing, right? We know that a Hamiltonian path exists. So these problems can be solved, but they will be solved in non-polynomial time. They are called NP complete problems. So to say you have a network of n nodes and the output is yes, there is a cycle existing which visits every node. Okay, and no, otherwise basically there is no cycle existing. Eulerian problem is a polynomial problem. So again, you have an input with n nodes, and you can say, yes, there is a cycle existing, which visits every edge in the network, and no otherwise. So you can already say no very quickly using the proof that Euler has come up with, which essentially says if you have odd degrees, then the cycle doesn't exist. So there are certain other things that Euler suggested, how one can actually say whether a path exists. And we can use these theorems to come up with a simple algorithm to do genome assembly or finding the Euler path. Because if you find an Euler path in a given uh, De Broglie graph, then that essentially that Euler path represents the walk, the Eulerian walk or the genome sequence itself. All right. So first, let's define certain things that allow us to apply the Euler's theorem. So we are working with directed graphs because whenever we are connecting two graphs or with an edge or connecting two nodes, we know that this particular node is the prefix node and the following node is the suffix node, because that's how the DNA fragments or the k-mers are overlapping. So in degrees, the number of edges into the graph, into the node, and out degrees, the number of edges out of the node. A graph is balanced if for every node, the in degree is equal to the out degree. All right. So for example, for this node, in degree is 1, out degree is 1. This node in degree is 1, out degree is 1. For this node, in degree is 2, 2 arrows coming out, out degree is in degree is 2, 2 arrows coming in, and out degree is 2. Right. So a balanced graph is where every node has equal in degree and out degree. Okay. So first, as you can imagine, Euler's theorem says that for a graph to have a Eulerian path, the graph should be balanced. The second thing is that for Euler solution to exist, the graph should be strongly connected. That essentially means that for a graph, you should be able to reach every node with any other node. Okay. So for example, this is a strongly connected graph. So each node you can visit with any other node. This, for example, is a strongly disconnected graph where it's very clear that if you are in any of these cycles, you are not going to be reaching these other 4 nodes. Okay, so again, Euler's theorem says every balanced, strongly connected graph has an Eulerian cycle. Okay, so the proof is what's called this is like a proof that you have to actually do yourself. So you can actually start to just implement the idea. So the proof that Euler came up with said that let us start from any balanced, any node in the balanced sort of graph. So let us say he said that let's put a ant placing on any of the nodes. You just randomly take a node. Okay. Now the ant is here and it starts to take a walk. And you start to walk until you reach the same node. Okay. So when the ant will get stuck, that is essentially it's going to reach to the same node, then you essentially change randomly and you place the ant somewhere else. So I'll show you how it works. So let us say the ant was starting here and it took this path and it's come back to V0 again. Okay, because the graph is balanced, so it will eventually get stuck. So now what do? You place the ant somewhere else randomly. So you place it on some other node which still has in degrees and out degrees left, right? So let's say the ant was placed here. And then the ant starts to walk. It can only go in this direction. Then it goes in this direction. Now it has a lot of choices. So let us say it can go in any of these directions. So this or this, let's say it goes on this one. Then it goes back like this, like this, and then it gets stuck again. Right? So when you do this, then eventually uh, this path is again exhausted. Then you do it again. You place the ant somewhere else, let's say on this one, and then you finally cover all the edges. So now by doing this iterative process, you have basically connected all the edges, right? And when you do this, then this suggests that the Eulerian cycle will exist in a graph like this. Okay, but why do you think we can be sure that this process will use all the edges? Is this clear? Is the Eulerian sort of proof sort of clear for you? How you would prove it? How you would check whether the Eulerian cycle will exist in a strongly connected balanced graph? It's class of proofs which are basically proofs by doing. So the next question is, why do you think this proof is going to work? Why do you think that this process will always work for all the edges? We'll be using up all the edges here. It's simple, right? Because it's the graph is strongly connected, right? And it's balanced. So the in degrees and out degrees are the same. So you will never going to exhaust all of them unless all of the in degrees and out degrees or all of the edges unless you have actually visited all the edges. Okay, because the graph is strongly connected. So when we have both these conditions met, you would see that you will be visiting all the edges because in degrees and out degrees are common. And you can see, try to make a graph by yourself and keeping it balanced and strongly connected, you will see that the graph will always have a Eulerian cycle. Okay, so this graph does not have this undirected graph does not have a Eulerian cycle because as you can see, there are whenever you have odd edges, right? Odd degree. So this odd degree is basically meaning that the number of edges that are coming are odd. So when you say that a graph is balanced, that would essentially mean that the number of edges will always be even. So clearly the number of edges are odd. So you can clearly say that for this graph, there would be no Eulerian path. Now, can you tell me, or you've already found this, right? How can we make this into an Eulerian graph?
Sir, by adding any other edge,
Okay. Can you add any other edge?
like either add or remove any edge.
So you've already found out, right, that one edge was always remaining,
Yes.
right? They could do 6 bridges. So if you remove one of the edges, then most likely this problem is going to become, it's going to have a Eulerian cycle. Can you tell me which edge will be the best to remove here?
Sir, I think any edge will work.
Any edge will work?
Yes, sir.
Removing any edge will work. Are you sure?
Totally the one between green and orange.
So if you want to remove this edge, then the in degrees and the degrees will become, the graph will become balanced because
Yes.
the in degrees and out degrees will be the same. Everything will be even, and it's already a strongly connected graph because you can reach anywhere from anywhere, right? So in order for, so Deepak was right earlier when he said that you can actually remove any edge and it will work, have a Eulerian cycle. But in order to you to be sure for the Eulerian proof, I think you'll be removing this middle one, right? Because then the things will become uh, so this is what's called a constructive proof, meaning that you have
So even
to
after removing one edge, how was it balanced exactly? Because like the
these are
blue
odd.
and the red ones still have
Yeah,
three.
these will always be odd. Yeah, I was waiting for somebody to say that. Yeah, so that's not the case, right? So any edge you can remove and it would be the same. So this is what's called a constructive proof, which essentially means that if you can come up with an algorithm to find the Eulerian cycle, then that means algorithmically you can solve the problem. So then that means the cycle exists. So how do you do it? You are given a graph. You start with an arbitrary node in the graph V. A cycle is basically a short walk starting at V and visiting all the edges until there is a cycle. That means you come back to the edge. So while there are unexplored edges in the graph, you have a new start. The node in the cycle, so node in the cycle with unexplored edges, cycle prime, right? So it's a new cycle formed by when we transfer after you have traversed the cycle, having a new start and then randomly walking, and then you'll keep on adding these cycles, right? So every time you'll get a new cycle. So as soon when you finish this, you have a new cycle, then you go to another unexplored edge, you have a new start, and you start to walk on unexplored edges, then you get a new cycle, and you keep on doing this until there is no unexplored edges left. So this is the simple algorithm for the Eulerian cycle. Okay, so now how do you actually do this? You do this computationally by representing the graph in two ways. The one way of representing a graph, a directed graph, is by what's called an adjacency matrix. So adjacency matrix, basically whenever you have a connection, an edge between two nodes, you basically would be putting one there, and then where there is no connection, you will be putting a 0. So let us say there are 5 nodes here, A, B, C, D, E. So because there is a edge from A to B, you put a 1. All right. But there is no edge from B to A, right? So this is a 0 here. So whenever it's going from A to B, so from the prefix to the suffix, then you put a 1 there. So similarly, you have A to E, so there is a 1 here. Now there is D to A and there is C to A coming here. So if you go for this, so you have 1, 1 here. All right. So your rows are basically where edges are coming out. Your columns are where the edges are coming in. All right. So an adjacency matrix, 1 if there is an edge connecting the node I to node J, otherwise it's 0. The same way of representing this in so this is a simple matrix, right? The same way of representing this would be what's called an adjacency list. So this data structure is called a linked list data structure. I hope everybody knows about linked lists. Were you introduced about to linked lists? Yeah. So instead of having 1 or 0 representation, you basically store the address of the physical pointer to the node. And so basically A would be having pointers to B and E, B would be having pointers to C and D. So these are basically actually storing the nodes. All right. So now, given these representations, it's quite easy to apply the algorithm that I showed earlier. You can either go in the matrix fashion or you can actually go in the linked list fashion. So in the agency lists, essentially you will be having dictionaries, right? And just like I showed you dictionaries earlier, where instead of having storing numbers at each of the node, each of the sort of dictionary key values, so numbers there were representing where that particular keyword is being found in a letter, in a word, in a sentence. Here you are actually going to store pointers to the location of those letters themselves, those keys themselves. So key is the node I and value is the list of nodes that I is connected to. So how do we find a Eulerian path in this graph? Does this satisfy? So we know that it satisfies the condition, the Eulerian path does exist here, and it satisfies one condition, that it's a strongly connected graph, right? Because you can reach every node from the other node. But does it satisfy the first condition?
Sir, how is it strongly connected if we are taking directionality into account?
So why is it not strongly connected?
So you can't reach like the first one, that is TA from TT. Say.
Exactly. So how can you make it into a Eulerian graph now?
Sir, we can like remove directions or add a node from TT to TA.
Exactly. So when you add a node from TT to TA, you complete the cycle, and then TT and TA and TT, both of them have similar, become balanced edges, and this graph basically becomes a balanced graph. Okay. So whenever you are given a graph and you have to check whether Eulerian cycle exists, you essentially connect the edges which might be unbalanced, adding one or two edges, and then you will be checking whether the Eulerian, whether the graph becomes balanced or not. Okay, so now why will the augmented De Bruijn graph on the right be balanced for any pattern of collections? You know this, right? Because you can reach any node from any other node now. Okay, for every node V in the De Bruijn graph, the in degree and out degree are both equal, and therefore the number of prefix and suffix, right? So there are two prefix and suffix for each of these nodes. So the string reconstruction problem basically can be solved using De Bruijn graphs now. So what was the problem? You have been given integers k and a collection of patterns of k-mers, right? And the output is supposed to be the text, which is equal to the k-mer composition of equal to patterns. So the first step is you form the De Bruijn graph from patterns. This was quite clear. You take your patterns, your k-mers, you break them into two nodes connected by the edge. You keep on gluing the nodes until there is nothing else to glue, all the similar nodes. So you will get the De Bruijn graph. Then you add an edge to modify the De Bruijn graph into a balanced De Bruijn graph, right? Into the edges where the in degree and out degrees are not balanced. Then you find a Eulerian cycle in the balanced graph. You know where to start because you already know beforehand when you have G which of the edges are having no in degrees and which of the edges are having no out degrees. So you know already where the graph ends. And if you infer the Eulerian path, basically given the cycle exists, you can infer the path by basically starting in the cycle at those two nodes which are unbalanced. All right, is this clear? You convert this genome part into the string text. Is this clear for everybody?
Yes, sir.
So given, if I would ask you to make a De Bruijn graph from patterns, given patterns, and then uh, make all this like intermediate things like the De Bruijn graph, the balancing of the De Bruijn graph, then finding the Eulerian path in the De Bruijn graph, and then converting that path into a text. I hope everybody can do it now. Not just two people.
So I just had like one doubt. So how did they find the unique path that connects every node like exactly once? That wasn't like very clear to me.
So you need to know that there is basically going to be one path existing, right? So if the Eulerian cycle
Yes.
exists, then the path will exist, and I'll show you how. The next class maybe, after I've discussed this.
So, but like, if you consider the like the AND method that you gave, so we
Yeah.
randomly initialize the AND at any point and see when it comes back to the initial position.
Yes.
So, how do you get the Eulerian path from that?
So that basically means that cycle is not the right. I'll explain it in the next class.
Oh,
I'll
fine.
discuss the algorithm, the Eulerian path algorithm in the next class. But if the graph is Eulerian, then you can find a cycle, and there's a clean algorithm for that. Okay. So besides that, okay, these things are true. All right. So now so there were certain assumptions that we took initially, if you remember in the last class. The assumptions were that the reads have perfect coverage. That means when you are breaking down your DNA molecule, you will get all possible k-mers, but that's not always the case because this is random sampling and sometimes some k-mers might be lost. We assume that all the k-mers would be exact representations of the original DNA molecule. There will be no errors, but in reality, there are errors. So the reads are error prone. For example, if the clustering is not happening properly, if the two clusters on the Illumina machine, they are close to each other, Then sometimes there are overlaps of clusters and you get cross contamination of signal from the two clusters. So that becomes a problem. The exact number of times a k-mer is supposed to be found is unknown. So this is the problem of multiplicities of k-mers. And we definitely know that the DNA is double-stranded and it consists of multiple chromosomes. And each chromosome might also be in multiple copies. So for example, for us, we have a maternal copy and a paternal copy, right? So these are some of the challenges. And in the next class, I'm going to discuss about how do we overcome these challenges, and specifically we'll start with how do we actually have a Eulerian cycle. Okay, so for tomorrow's quiz, it will be until this part as well. Again, I'm not going to ask you to make the whole thing, but the basic concepts of how things are constructed, what are the certain assumptions being taken in different kinds of the two problems, Hamiltonian and Eulerian paths. So these are the basic things that I would be asking about. More questions about actually constructing things, finding the Eulerian paths. Those are problems that will be asked in the in the minor. All right. I'll stop the
Yes,
class
sir.
and I'll take questions if there are any.